Hello, fans of GeoGebra. We have, I think, a very unique method of analyzing a two-dimensional truss. And admittedly, it may seem a little fussy for the complicated truss that I will show you, but I think it's pretty straightforward for the simple truss in front of you. So we have a three-bar truss that has two reactions at the left and one reaction at the right, a vertical reaction only, which means that this point can slide horizontally freely, but it cannot move up and down. And we have some arbitrary load on it. Here the load is vertical. And the question is, what is the bar force on the lower chord, force AB? The technique is always the same in Muller-Breslau. You take the force of interest multiplied by some displacement that you are enforcing. If that's a moment, this would be a rotation in the bar. If it's a shear, it would be a relative translation of the two pieces of the bar. But if it's axial, you just cut the bar and open it up, some gap, delta. And then you just watch what happens. You watch the external loads as they move due to this perturbation. They have work. If the movement is in the direction of the external loads, that work is positive. If the movement opposes the direction of loads, that work is negative. And then that's it. You just divide by delta and you have the answer. So in GeoGebra, you label the segments AB, AC, and BC, and then you don't have to say anything like length of AB or length of AC. The definition is that the length is within the name. It's a magnitude. So how do we start this off? Well, I drew a circle around A. Since I'm looking for force AB, I need to elongate that bar by delta. And here delta is 1. And I know A is not moving, so I draw a big circle centered on A of radius AB plus delta. And as I said in the onset, B cannot move vertically, so B is somewhere on this horizontal axis, and here it is. It's at 21, which makes perfect sense. Then you need two circles at this point for the intersection of the two circles to establish that new crown. The first circle is radius AC, which is centered on A. And the second circle is radius BC, which is centered on BB, not on B, on the new point BB. And obviously there's two intersections here, but this lower one is below the ground. I don't need that one. So I'm calling that CC. Ladies and gentlemen, there's something kind of amazing at this point though. In 2D, that is always the trick here, that you will use two circles to establish the new or subsequent point. If this were a 3D truss, a space truss, you would have the intersection of three spheres, which is pretty head exploding. So let's just stay in 2D for now. It's the intersection of two circles. Those of you who have studied Muller-Breslau Method 125 years ago might remember this as the tangents to the circles being the small angle displacement. But here I have a very, very large displacement. And I just map this movement. So notice how C is dropping because BB is moving. So let me show it over here in GeoGebra. If the delta is really small, you could see that the crown doesn't move vertically a lot. If the delta is very big, the crown moves a lot. And I'm only tracking the vertical displacement because work has to be done in the direction of the load. So I have a vertical load. I'm tracking the vertical displacement. So here, the vertical displacement would be 0.91 but then it gets smaller and smaller and smaller. And then I use this equation, which I showed you, the force AB times this perturbation is equal to the external work done. And you see that as we get smaller and smaller, the theoretical answer is 1200. And as we get smaller and smaller, we asymptotically approach 1200. And I think that's quite beautiful, I think, right? So that this technique also works for lateral loads too. So not just gravity loads, but gravity and lateral. So here's the same truss. The theoretical was 1550. And starting off with a very large displacement. Now notice what my external work is. I need the vertical movement of C linked to load 1, and I need the horizontal movement of C linked to load 2. And that would be load 1 times del vert C plus load 2 times del horizontal C. All of that divided by my arbitrary perturbation, delta, and I get the answer. So we said 1550 is the theoretical answer. So let's take a peek at that. So here is 1700, pretty good even for this wildly large displacement. Remember, our 1550 was our answer. Notice that I'm tracking the horizontal movement and the vertical movement, which is super easy. I just take the abscissa of this and the abscissa of that and the ordinate of this and the ordinate of that. Abscissa and ordinate, that's pretty cool. And then 1550, of course, is our theoretical answer. I could probably make this negative, this delta, and then I would have like a singularity. It would flip signs. Okay. So then things get a little fussy here when we have a more complicated truss. And this is gravity only, but I did a more complicated truss to see if I could do it. And it does work, but it's slightly twitchy at the end, and I'm a little bothered by that. But I just thought I'd share this anyway right now with the internet. So here we have a more complicated truss and the same idea. So now I'm going to draw a circle of EA around A, and I'm going to drop E somewhere on that circle. I don't know where E is. So that's what I'm going to do. I'm going to drop this point somewhere on this circle. And then from EE, I go towards B, and the length is not BE, it is BE plus delta, because I'm looking for bar 4's BE. I didn't say that in the beginning. I'm looking for bar 4's BE in this truss. Nothing magic about BE, I just chose that one. So notice that this next circle is starting at EE as the center, and the radius is EB, or BE here, sorry, plus delta. And delta happens to be 1 for me here. So I'm left of the original B at this point. But it depends on delta. And notice that at this point, you need to do that 2-circle intersection for subsequent points. So I'm starting at BB as a center, and now I have a radius of DB. Starting at EE, and I have a radius of ED, and I'm looking for D. So notice what I did. Starting at BB, I have a radius of DB. Starting at EE, I have a radius of ED, and I'm looking for the new point D. And I'll call that DD. And there it is. I think it's a good idea to periodically wiggle this just to see if everything is working as a rigid mechanism. So what I mean by that is, are things really responding as they, as a machine, as a rigid link would here, right? So here I'm jumped ahead a little bit, but I'm looking for DD, and you see everything is kind of alive. Now notice what happened here, and I think this is a good way of doing it, but I haven't quite decided yet. I have an extra equation because I have only really one more point here. I found DD, I have found BB, I found EE. A is not moving, so all I really need is CC. But I can get CC from the intersection of, let me scroll up here and I think it'll make more sense. I can get CC from the intersection of the CD centered on D and the EC centered on E, or I can get the new C point from EC centered on EE and AC centered on A. So that's what I did here, and I don't know if that's the best idea or not, but I did it. And I came up with, you'll see it maybe live over here. So I have these circles here. So let me show you these circles here. This is radius DC, so that is centered on DD. This is radius EC, that is centered on EE. And then the last one is radius AC, and that is centered here. And now you see the dilemma here that I have, where they all meet, that's the answer right there. But until they all meet, you kind of have this dilemma, I guess, is probably the definition of that, right? So what I did was I mapped the error, how much error, so that I'm not solely relying on my eyes to notice when are those blended together. And the error probably should be the square root of the sum of the squares, now that I think about it, of x and y. I just chose y just because I'm just did it. And, I figure, okay, that's probably good enough, right? And here's the bar force, which is not correct. I have 1469. The answer is 1200. The answer is 1200 in this case, the theoretical answer. But notice I still have a very large delta here. I have a very large delta. So what I did was I lowered the delta. Let's say it's a half a foot. I'm using feet, the United States imperial units, which we and Rwanda are using right now. And I could wiggle this again for the half foot displacement, and boom, that looks pretty good. And the answer is 1200, remember? And that's pretty good, right? Or I could knock it down a little bit more, maybe let's say 0.25 feet. That's my perturbation. And then I visually wiggle this until it works, and that's pretty good right there. And this is where it gets a little twitchy, and I'm not 100% sure why. So if you know why, let me know. So let's say 0.1. Nice even number there. And a very, very small perturbation. And, the answer is supposed to be 1200. So I think I'm zooming in on the answer. But I don't exactly know why it's, like, if I just keep going, I think it just gets super sensitive, and maybe that's the problem, is that I just can't get, let's say it's 0.1, my perturbation, right? And then I'm really tweaking this thing. Now my answer is kind of nutso, because I think my errors are, I think I'm zooming right through that singularity, but I'm not 100% sure. So, let's talk internet and figure this out. Super exciting use of Muller-Breslau in trusses.